Welcome back to another explainer. Okay, let's just dive right into this. Have you ever stopped to wonder how the invisible, totally chaotic motions of microscopic particles actually create the tangible world we live in? Well, today, our goal is to unpack this chapter and build a conceptual bridge. We're connecting the invisible microscopic motion of atoms to the macroscopic stuff we experience every single day, like the pressure in your car tires or the temperature of the air around you. We're going to demystify the kinetic theory of gases.
It's kind of a wild question when you think about it, right? If we literally cannot see atoms, how on earth do we know they make the rules for the whole physical world? Today's explainer takes us on an incredible journey. We're going from ancient philosophical ideas about the invisible all the way to the measurable, visible world that modern science has mapped out. We'll see exactly how humanity figured out there was this hyperactive microscopic universe without ever even laying eyes on it.
So here's the roadmap for today. 1. The atomic hypothesis. 2. The macroscopic gas laws. 3. Inside an ideal gas. 4. The meaning of temperature. And finally, 5. Degrees of freedom.
Starting us off with Section 1, the atomic hypothesis.
You know what's truly amazing? The sheer span of time this idea covers. The concept that matter isn't just one solid, continuous block, but is actually made of tiny, separate pieces has been around forever. Back in the 6th century BC in India, Kinetic proposed indivisible atoms. And over in Greece in the 4th century BC, Democritus suggested the exact same thing. I mean, the word atom literally means indivisible in Greek. But you know, these were really just intuitive guesses. Fast forward to the early 1800s, and John Dalton formalizes the scientific atomic theory based on chemical proportions. And then finally, in the 19th century, brilliant minds like Maxwell and Boltzmann developed the kinetic theory. They took these static atoms and gave them dynamic, mathematical motion. It's literally the culmination of millennia of human curiosity.
To really wrap our heads around kinetic theory, we've got to play with scale for a second. In solids and liquids, atoms are packed super tight, like about 2 angstroms apart. An angstrom is 10 to the power of -10 meters, extremely tiny. But in gases, the interatomic distances jump to tens of angstroms. But here's the real kicker, the mean free path. That's the average distance a gas molecule travels before bumping into another one. In gases, that distance is thousands of angstroms. This wide-open, super sparse environment is exactly why gas molecules can just act independently, and it's why their behavior is actually a lot easier for us to understand than solids or liquids.
Moving right along to Section 2, the macroscopic gas laws.
All right, this brings us to Boyle's law, which goes way back to 1661. It basically says that if you keep the temperature constant, the pressure of a given mass of gas does the exact opposite of its volume. Squeeze the gas into a smaller box, and boom, the pressure goes up. The experimental data for steam actually matches these theoretical predictions beautifully, especially at high temperatures and low pressures. Under those specific conditions, real gases act a lot like an ideal gas because the molecules are just so far apart that they barely interact with each other.
And then we have Charles' law. This one tells us that if you lock in the pressure, the volume of a gas is directly proportional to its absolute temperature. Heat it up and it expands. Once again, real-world observations map perfectly onto these theoretical laws. They act as visible anchors for all the abstract math, showing us that the experimental data clearly, undeniably aligns with the equations.
Okay, before we shrink back down to the microscopic level, I really want you to just absorb this number. 6.02 times 10 to the 23rd. That is Avogadro's number. It tells us that in just 22.4 liters of any ideal gas at standard temperature and pressure, which, by the way, is roughly the size of a large beach ball, there are this many molecules. It's a staggeringly massive number. Understanding this sheer massive scale is absolutely crucial if we want to realize how millions of tiny random events can just average out to create perfectly smooth, steady pressure.
Which brings us to Section 3, inside an ideal gas.
So to actually make the math work, without losing our minds, physicists came up with a theoretical model called an ideal gas, and it has a few key assumptions. First, we assume the molecules are so spread out that intermolecular forces are basically negligible. They just zip around freely in straight lines until they hit something. And when they do hit the walls or each other, the collisions are completely elastic. That means zero energy is lost to heat or deformation. The total kinetic energy and momentum are perfectly conserved. Now sure, no real gas is truly ideal, but at low pressures and high temperatures, they get remarkably close to playing by these rules.
So, how exactly do all these tiny bouncing balls create the pressure we feel? Let's walk through the mechanics. Step 1. A tiny gas molecule hits the wall of its container. Step 2. Because it bounces back elastically, its velocity reverses, which means its momentum changes. Step 3. Well, Newton's laws tell us that a change in momentum over time exerts a force. So that one tiny molecule exerts a microscopic push on the wall. Finally, step 4. When you multiply that tiny push by the billions and trillions of molecules that are constantly bombarding every single inch of the wall every fraction of a second, the sum of all those forces equals the macroscopic pressure we can actually measure with a gauge. It is the ultimate example of microscopic impacts scaling up to macroscopic force.
And listen, these molecules, they are not just lazily floating around. 516 meters per second. That is the root mean square speed of a single nitrogen molecule in the air around you right now at room temperature. Just let that sink in for a second. That incessant, random motion is happening at roughly the speed of sound. The air might feel perfectly still to you, but at the microscopic level, it is a chaotic, high-speed storm.
All right, section 4, the meaning of temperature.
Because temperature isn't just some random number on a thermometer, the kinetic interpretation reveals a profound truth. The average kinetic energy of a molecule is directly proportional to the absolute temperature of the gas. They are essentially the exact same thing. When you touch something and feel that it's hot, you are literally feeling the high average microscopic kinetic energy of its molecules. The equation tells us it's independent of pressure, volume, or even what kind of gas it is. It is purely about the energy of motion.
To really lock this idea in, the chapter we're looking at provides a fantastic analogy. Picture something macroscopic. Imagine a heavy cricket bat, maybe swung by the great Sachin Tendulkar, hitting a moving ball. Because the bat is moving towards the ball rebounds significantly faster than when it approached. Now, shrink that entire scenario down to the microscopic level. If you push a piston to compress a gas, that moving piston acts exactly like the cricket bat. A gas molecule hitting the moving piston will rebound with a higher speed, which means it has a higher kinetic energy. And since we just learned that kinetic energy is temperature, the gas heats up. It takes a really complex thermodynamic concept and just turns it into an intuitive physical action.
And finally, that leads us to section 5, degrees of freedom.
Up until now, we've basically been picturing molecules as simple little dots zipping around in straight lines. But consider a diatomic molecule, like oxygen or nitrogen. Think of it like a tiny dumbbell with two atoms joined together. It doesn't just move left, right, up, and down. It can also tumble and rotate around two independent axes. And this is vital because rotation is motion, and motion is kinetic energy. This molecule has totally new additional ways to hold energy compared to just a simple single atom.
We call these independent ways of moving degrees of freedom. You've got translational movement, that's flying in straight lines along the x, y, and z axes, and then you've got rotational movement, tumbling around. Now here's where it all comes perfectly together. The law of equipartition of energy states that in thermal equilibrium, energy is shared equally among all active degrees of freedom. So every single way a molecule can move gets an equal slice of the thermal energy pie. Because diatomic gases have rotational degrees of freedom, they literally have more active slots to put energy into. Therefore, a diatomic gas actually holds more total internal energy at the exact same temperature than a simple monoatomic gas. The actual shape of the molecule dictates how the bulk gas behaves when you heat it. How cool is that?
So, we started with ancient philosophers guessing about indivisible atoms, and we've built this massive mathematical bridge to explain everyday pressure and temperature. But as this chapter points out, atomic theory isn't the end of the road. It's really just the beginning. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons, and those are made of quarks. And hey, maybe quarks are made of vibrating strings. If atoms aren't the end of the story, what invisible worlds are we going to discover next? Nature always has surprises for us, and the search for truth is just infinite. Thanks for joining me on this explainer, and keep questioning the invisible.